All right, good afternoon, everyone. Hello there. Welcome to the Academy's Morrison Planetarium and to this presentation of our final show of the day, a very special presentation that we call the Tour of the Universe. Now, how many of you have seen our other shows that we offer today, Dark Universe or Expedition Reef? A few of you. Okay, this show is quite a bit different. It's not a pre-recorded show. It's all live, so you'll hear my voice throughout. And what this show consists of is a trip through a model, a 3D model of the universe. So we start at the Earth and just back away and see how far out we can go. So we're going to see where we are in the big picture of things, where we are in the solar system, where we are in our galaxy, and where we are in the overall distribution of galaxies in the entire universe. And our vehicle for making this voyage through space is a piece of NASA-supported software called OpenSpace, which you can actually download for free and install on your own computer if you want to give it a try. So if you like what you see here on the dome overhead during the next half hour or so, come and see me afterward, and I'll tell you how you can get a hold of this software, which is completely free, and you can try it for yourself. Now, as with all of our presentations, we do ask that you please refrain for the next 30 minutes from eating, drinking, snacking, any kind of photography or recording. This would also be a great time to silence your personal electronics and to tuck away any light-emitting devices like cell phones, tablets, cameras, flashlights, etc. That light can be very distracting to the people sitting around you in the dark and can also interfere with the images that we project onto the dome overhead. At the end of the show, we ask everyone to please exit out through the doors at the top of either stairway. If getting all the way up these stairs is going to be a problem for any of you, especially from the lower rows, just stay in your seat at the end and our staff will assist you out the lower exits if that's more convenient. But everybody else, please use the doors at the top. And this is a live presentation. I'll be flying us live through our database of the universe. I'll try not to fly too wildly, not fly into, crash into any planets or fly into any black holes. However, if you do find yourself feeling a little funny because of the immersive nature of the planetarium experience, the image goes all the way out to your peripheral vision. If that makes you feel uncomfortable at any point, just close your eyes for about a minute or so, and any discomfort should go away. So hopefully just keep that in mind. And in just a minute, we're going to darken the room and start our journey into outer space. Now, we're going to begin our trip at a we'll call it a mystery location, because it's something that I'm going to have you see if you can guess where it is. So we'll drop our lights and see where we might be on the surface of the Earth. Have any idea where we might be? There's a place called Foster City, which is just down the peninsula, not too far away from San Francisco, but it is along the flight path of SFO, the airport. And I don't know why they put the name of the city there on the ground. I guess so pilots flying into the airport know where they are. I don't know. We'll have to look that up. I've tried. It's not an easy thing to find out. But we're about 1 kilometer above Foster City, which is close to San Francisco International Airport, one place where a lot of people take off on trips around the world, but we're going to go even higher than that. We're going to travel up to the edge of outer space. And one famous astronomer once said, outer space is not that remote. It's only an hour's drive if cars could go straight up. Which is true, because the officially recognized boundary of outer space is 100 kilometers above the surface of Earth. That's about 62 miles. So roughly the distance from San Francisco to San Jose or San Francisco up to Santa Rosa. That height, that altitude, is the official boundary of outer space. Why did they pick that? I mean, is there a sign that says outer space begins here? No. As you travel higher and higher into the atmosphere, the air gets thinner and thinner and thinner and thinner. And finally, at about 100 kilometers or so, the air is so thin that control surfaces like wings, rudders, flaps, those don't work because there's not enough air for them to work against. So up at this altitude, you have to use rockets to maneuver. Now, the atmosphere is not, it's not a constant width or density. It does expand and contract. And so sometimes the boundary of outer space fluctuates just a little bit. For some purposes, NASA even uses 50 miles rather than 62. But generally, safely, 100 kilometers is thought to be above most of the atmosphere, so that is the nice round number that the International Federation of Aeronautics uses. But we're going to go even higher than that. We're going to go above 100 kilometers, about 4 times that, so hang on to your hats, here we go. A little bit higher than this. And at 400 kilometers, this is the altitude at which the International Space Station orbits, about 250 miles above the surface. So this is now an astronaut's view of our planet. So we're traveling eastward across the United States, and you can see a number of things. There's Lake Mead down here, the Grand Canyon. You can just barely see right there. Interesting view of our own planet. But now, we're going to go even farther from Earth than the International Space Station, which is only one of many tens of thousands of satellites that are orbiting around our planet. We're going to travel so far out, we'll travel as far out as humans have gotten from our planet. We'll travel, let's see, about 1,000 times farther than the International Space Station. So we're going to go about 250,000 miles away from our planet, which is as far as astronauts got in the late 1960s and in the 1970s. Between 1968 and 1972, NASA ran the Apollo program, which sent astronauts to the moon, and we can see the moon appearing over to the right, way over right there, and we'll center ourselves on the moon itself, right there, and then move in. Now, it took the Apollo astronauts about 3 days to get to the moon. We're traveling a lot faster than that, because we don't have the time. We don't have 3 days. But here's our own satellite, which is a large ball of rock about 2,000 miles across. You can see that it's got countless craters all over its surface. Those craters were blasted out by the explosions and impacts of asteroids and comets during the moon's history. And there are so many of them there, you can't count them. Some of them are very large. For example, a couple of the ones right in the center of our field of view there, they're about 100 miles across. And they make up the lighter colored areas, the more rugged highlands of the moon's surface, as they're called. The dark areas, the dark flat areas, are called maria, which is a Latin word and means seas, because early astronomers used to think that those were bodies of water. They didn't have telescopes that gave them a good, clear view of what the moon looks like up close. They thought those dark areas were bodies of water, so they called them seas and oceans, and they gave them really beautiful names like the Sea of Tranquility, or the Sea of Rains, or the Sea of Serenity. But today we know that they're not bodies of water at all. Those large, flat, dark areas are areas where lava or magma bubbled up from below the moon's crust about 1 billion or so years ago, spread out, covering the area around them, and cooled and hardened into these flat plains of rock. So those are not seas of water at all, but if you want to call them seas of rock, you can do that. But that's our satellite, the moon, and there are plans to return to the moon in the next few years or so. The NASA plans a project called Artemis, with which we'll be sending humans back to the surface of the moon, and that should be taking place as currently planned in the next few years or so. But let's travel out even farther away than the moon, which took the Apollo astronauts about 3 days to get to. It took us just a matter of seconds. But we're going to have to travel even faster than that. As we travel farther out into space, we're going to encounter objects and distances that are so far out that measuring their distances in miles is kind of ridiculous. The numbers just get too big. It's like trying to measure the length of Golden Gate Park in inches or millimeters. So what we're going to do is we're going to use a different scale, one that is based on the speed of light. That's something that astronomers use as a very convenient measuring tool. It tells them a number of things. It tells them not just how far away things are, but how long it takes the light from those objects to get to us. It takes light or radio waves, which travel at the speed of light. It takes that about 1.5 seconds to get from Earth to the moon. It takes light about 8.5 minutes to get from Earth to the sun, and likewise back and forth. One-way trip is about 8.5 minutes. So when you look at the sun in the sky, there in the middle of our solar system, you're seeing the sun when it emitted that light that you're seeing right now 8 minutes ago. So you're looking back into the past by about 8.5 minutes. When we look at other planets in our solar system, we're seeing objects that are light hours away. So this is our overhead view of the solar system, with the sun in the very center, our own star. The nearest planet is Mercury, and then comes Venus. We on Earth are the third planet out, and then comes the red planet Mars. Those are the innermost planets, called the terrestrial or rocky planets, because they're made mostly of rock, and they're fairly small compared to the other planets. Now, right after Mars comes an area that's filled with a lot of debris, chunks of rock and metal that are believed to be leftover material from the formation of the solar system. This is the main asteroid belt, and there are tens of thousands of objects out here. And there are some asteroids which are not restricted to this main belt between Mars and the next planet. Some even travel through the inner solar system and pass close to Earth. And those are the ones we want to keep an eye on because they have the potential to impact Earth. But as we travel even farther out from the sun, past the asteroid belt, we encounter the large planets of the solar system, what are called the gas giants. And these are Jupiter, and then Saturn, and then Uranus, and then Neptune. Those are the 8 planets of our modern solar system. The planet, what used to be called the planet Pluto, is no longer recognized as a planet in the sense that we've just seen the other worlds in our solar system. It is now classified as a dwarf planet, and that classification was made in 2006 when astronomers decided that Pluto is just a different kind of object. Maybe we should give it a different kind of category. So it's in its own class, along with a few other dwarf planets out there. So here's the orbit of Pluto way outside, and you can see how highly inclined or how tilted it is with respect to the orbits of the other planets of our solar system, which are pretty much on the same plane, but Pluto is tilted. It's inclined quite a bit from that angle. So astronomers thought that's one of the reasons that they wanted to reclassify Pluto as a different kind of beast. But now, as we travel even farther out, we'll find out that Pluto is, one of the reasons Pluto is considered not a regular planet is because, according to the definition of planet that astronomers came up with in 2006, it hasn't cleared its path of other small objects. It has, they said that a planet has to use its gravity to bully little guys out of the way. And Pluto hasn't done that, because this is what's also out there around the neighborhood of Pluto. This is an area called the Kuiper Belt, or the trans-Neptunian objects. And these are all objects that are kind of like the asteroid belt, only these are also comets, large chunks of ice which orbit around the sun, and also other dwarf planets like Pluto. There are several out here that are either dwarf planets or candidates to be dwarf planets. So there's a lot of stuff out here, and that's another reason why Pluto is considered a completely different kind of thing nowadays. But let's travel even farther out, and I want to show you one more thing, which is we've talked about how far out we can travel. We've talked about how far the space station is and how far out astronauts traveled to the moon. Now let's have a look at our most distant spacecraft. Now these are not pilot, there are no people on board, but these are robotic spacecraft that have traveled way out into space, and there are 5 which have officially left our solar system. The one going off by itself up toward the top is Pioneer 10, which was launched way back in 1973. And then going off in the other direction are Pioneer 11, which is one of the longer paths here, Voyager 1, Voyager 2, and then New Horizons, which is the spacecraft that recently went past Pluto back in just not too long ago. So these are our most distant emissaries from Earth, our spacecraft which have traveled so far out that some of them have been traveling for about 45 years. And yet, they haven't traveled as far as light can travel in one day. The most distant, Voyager 1, is about 18 light hours away. So it still has a way to go. And it's going to be a long, long time before any of these spacecraft encounter a nearby star, because the stars are so far away, as we're about to see. It's going to take tens of thousands of years to get out to those. So let's continue on our way, traveling farther out, away from our own solar system and traveling into interstellar space, the space between the stars. And the nearest star to us, Alpha Centauri, is about 4 1/3 light years away, which means that its light takes about 4 1/3 years to reach us on Earth. So when we look at that star in the night sky, we're looking 4 1/3 years into the past, seeing the light that left it 4 1/3 years ago, just arriving to be seen by us here on Earth. As we travel even farther out, we encounter stars that are even farther away. Of course, stars that are tens or hundreds of light years distant. And before we get too far off, I want to show you one more thing, which is our most distant artifact, the most distant evidence that humanity exists in the universe. And that is a bubble of noise created by our radio signals. This radiosphere is about 90 light years in radius, or about 180 light years across. And this is as far as our radio signals have traveled in the past 90 years or so. And some of them have gotten pretty far out. These are early radio broadcasts. Some of it is radio noise created by nuclear weapons tests and such. But this is as far out as any evidence of humanity has traveled into space. And there are some stars that are enveloped by this radiosphere. And if there are any civilizations orbiting on planets orbiting those stars, they might have picked up our radio signals. Maybe they know that we're here. But if there are civilizations on any stars that are on planets orbiting any stars that are outside the radiosphere, our radio signals haven't gotten there yet. So they don't know about us. They don't know we're here. So that's an interesting thing about the size of the universe and how far things can travel and the speed of light and radio waves. But let's continue traveling even farther out. We'll leave the radiosphere on so we can see where we are with respect to other stars and with respect to the entire Milky Way galaxy itself. Because up until about 100 years ago, astronomers thought that there was only one galaxy in the entire universe, the Milky Way. And then Edwin Hubble showed that there are other galaxies. There are lots of other galaxies far beyond the Milky Way. He showed us that the universe is a lot bigger. Not only that, he showed us that the universe is getting bigger still, because all the galaxies are moving farther and farther apart from each other. So 100 years ago, Edwin Hubble showed us a brand new view of the entire universe. And our Milky Way galaxy is just a small part of that. And we on the Earth, at the center of this radiosphere, are not at the center of the Milky Way. We're off near the edge, about 2/3 of the way out from the center. As we continue traveling even farther out, we'll see our Milky Way from a distance. It's a flat disk of about 100 billion stars, measuring about 100,000 light years across, from one edge all the way across to the other. The light of these stars takes about 100,000 years to cross the diameter of the galaxy to get all the way to the other side. So our galaxy is quite large, but there are other galaxies that are even bigger. As we travel into intergalactic space now, we see that the Milky Way is just one member of a small cluster of galaxies called the local group. Now, the local group contains about, one estimate is about 80 small galaxies. The Milky Way and another large spiral disk called the Andromeda Galaxy are the two largest members of the local group. But this is just a small cluster of galaxies in the universe. There are others that are even bigger. There are what are called superclusters that contain hundreds or even thousands of galaxies. And everything you see right now, on our dome overhead, everything you see here is not a star, but a galaxy. Each galaxy containing several hundred billion stars. Now, this is all based on actual surveys of the universe by astronomers over the past several decades, recording the positions and densities and populations of stars in different galaxies. So this isn't made up. This is the real thing, a real model of the distribution of galaxies in the universe. And as we travel even farther away still, we'll see that our model of the universe has an unusual shape. We're going to travel just far out enough so that we can see the shape of this model. It looks like a big hourglass, or like two big fans stretching out in opposite directions. Is this the real shape of our universe? Does it look like a big hourglass like this? No, it's not. In fact, this empty void here that has only a few galaxies in it between the two large fans, this is an area that hasn't been mapped well enough yet. This model of the universe tells us that we have a long way to go. Our work is not complete. We haven't seen all there is to see. And what's blocking our view here along this plane is the disk of our own Milky Way galaxy. Because when we're looking along the plane of the Milky Way, we're looking in this direction between the two fans. And there's a lot of dust and gas in the way that's blocking our view. That's why we don't see as many galaxies in that area. But eventually, as our technology gets better and our techniques improve, we expect to be able to see more galaxies out in these areas here and fill out our map in a more uniform manner. But this is, again, our latest information on the distribution of galaxies in the universe. The universe doesn't really look like a big hourglass or a big butterfly, but this is just our current information, our current model of the universe based on the information we have so far. As we travel even farther out, we see more and more galaxies at tremendous distances of about 10 billion light years. And finally, we come to these orange spots at the edges of the fans. Those are quasars, which are very, very bright, energetic objects, which is almost as far as we can see with our most powerful telescopes. Quasars are believed by some astronomers to be very young galaxies powered by supermassive black holes. More recent research suggests that quasars may actually be colliding galaxies, giving off tremendous amounts of energy. And that's a very mysterious area that requires a lot more research. The most distant thing that has been detected, even beyond the quasars, is a faint background radiation, this background radio noise, a faint hiss that comes from all directions, permeating the entire universe. This is called the cosmic microwave background, and this is the oldest light that we can see. This is believed to be the earliest light that was able to travel from one place in the universe to another, which was emitted about 380,000 years after what's called the Big Bang, when the expansion of the universe began about 13.8 billion years ago. This is as far as we can see, and this is not a map of objects. This is rather a heat map of the very early universe, showing us areas that are a little warmer than others. And it shows us the beginning of the differentiation of matter and the beginning of the formation of stars and galaxies. So this is the state of our knowledge of the universe, and this is as far as we can see, which means we've got only one place left to go, and that is back in to where we came from. As we do, it may occur to you that it seems we've put ourselves at the center of this model of the universe. Is that really where we are? Does the universe really look like this? Well, no, because it only looks that way, because we're the ones who made the model. It's based on our perception, our view looking all around us. And so if there were somebody else in another part of the universe looking all around in every direction, it would seem that their model of the universe is centered on them. So we're not really at the center of the universe. Astronomers don't think there is a center to the universe. But as we travel farther and farther back toward our point of origin, with all these galaxies that you can see, each one containing hundreds of billions of stars, some containing trillions of galaxies, how many of those galaxies, how many of the stars in those galaxies might be orbited by planets? Well, it turns out, according to recent research, many astronomers believe that most of the stars, if not all the stars in the sky, are orbited by at least one planet. And if we look at a map of what we have discovered so far, looking for what are called extrasolar planets in the universe, well, that map of extrasolar planets looks something like this so far. Our map of stars that appear to be orbited by at least one planet looks like this. So far, since about 1994, we've discovered more than 5,000 extrasolar planets. Are any of these places where life might arise, where life could evolve? We don't know just yet. We don't know very much about these exoplanets because they're so far away. Now, we do know that some orbit very close to their stars, and so they're probably too hot. Others orbit very far out from their stars, and so they're probably too cold. But you need a certain number of conditions to be satisfied to determine whether or not a planet is said to be Earth-like and might be able to support life like Earth has. It's got to orbit the right kind of star so that it doesn't give off a lot of dangerous radiation. It's got to be the right distance from the star, so it's neither too hot nor too cold, and that allows liquid water to exist. That's very important for life as we know it here on Earth. So a lot of astronomers think if you want to find life in the universe, look for the water, follow the water. As we move in closer and closer to the center of our solar system, back in close to the sun, we'll see that of all the planets that we've seen so far, the other 7 planets in our solar system, including the dwarf planets and the other exoplanets that we've seen elsewhere in the Milky Way, and possibly, likely, that exist in other galaxies. Out of all those worlds, there's only one that has the right conditions that allows life to exist, as far as we know. So, in our travels across the cosmos, we find that there is literally no place like home. So with that, as we return to our planet, the planet of our birth, our world, our home planet, the Earth, welcome back. Welcome back to the planet from which we came, a planet that is so special, where life exists in a fragile balance with its environment, that we need to take really good care of this one world, this one blue world that we have. So with that, thank you all very much. We hope you enjoyed our presentation, and thank you for touring the universe with us.